Hello everyone, welcome to Andy's Sky Dream. Today in this video I want to talk about Riemann Hypothesis. If you watched the last video, you knew that I used the Taylor series to prove that the Euler's formula is true. But then after I recorded that video, I thought that, wow, that was my limit. That was like, yeah, that's it, that's the end. But then I learned about this Riemann Hypothesis, and now I realized that, dude, this Riemann guy, he's the man. Riemann Hypothesis is such a complicated concept that it even took me several days to fully comprehend and understand what it actually means. And this is actually not the first time I'm trying to record a video explaining the Riemann Hypothesis. This is my third try. And I'll see if this time I can fully go over what Riemann Hypothesis really is and explain it well to you guys. So, what is the Riemann Hypothesis? Let's take a look. So when we talk about Riemann Hypothesis, we have to first look at a zeta function. And this zeta function was proposed by Euler. And this is what it looks like. It has two limitations. So for s, this variable right here, it has to be a real number, and also s has to be larger than 1. Why does it have to be larger than 1? It's because that only when s is larger than 1, the function converges, meaning that it approaches a limit. It approaches to a certain value. If it is smaller than 1, then it diverges, meaning it will approach to infinity. The function will just be infinity, and that basically has no points. So why don't we try to plug in some values? First, let's do when s equals to 1. Let me explain that why does the function approaches to infinity. So when s equals 1, what would the function be like? So this will be the function. And why does this approach to infinity? Well, it's very easy to prove. So first, if we rewrite this function, it will be, if we think of another series of numbers. So we copy 1 down first, and we copy 1/2. And then, let's put 2, 1/4, and 4, 1/8, and so on. So if we compare those two functions, if we compare those two equations, 1 plus 1/2, that is the same. 1/3 plus 1/4 is definitely larger than 1/4 plus 1/4. And also, 1/5 plus 1/6 plus 1/7 and plus 1/8 is definitely larger than 4 1/8 added together, right? So this, if we rewrite this equation, it will become 1 plus 1/2 plus 1/4 plus 1/4, that's 1/2, and plus we have 4 1/8, that's also 1/2, and plus 1/2 plus 1/2, and so on, so on. So from this, we can know that 1 plus infinite numbers of 1/2 will definitely equal to infinity. And this function, the zeta function, is even larger than 1 plus infinite amount of 1/2. So this function is larger than this, which means it's also equals to infinity. And this is why when s equals to 1, the function will approaches to infinity. But also, when s is 2, what would that become? Okay, so this is what a function will become. But then, if we rewrite this function, it will be 1 plus 1/4 plus 1/9 plus 1/16. Okay, so this is the function. And how do we know that it converges to a certain limit? This is because when we take a close look at this function, we will realize that each time the number is adding a smaller and smaller number, which means if we have a coordinate system right here, the first term, 1, will be this amount, right? And then 1/4 will only be like probably this much, and then 1/9 only a little bit more, 1/16 even smaller, even smaller. So from this, we can see that this function, when s equals 2, it is actually approaching to a certain value because it's adding smaller and smaller amount each time. So from this, we can get the conclusion that when s is larger than 1, it is approaching to a certain value. Well, at this point, you might be wondering which specific value does this equation converges to. The result for this equation is pi squared over 6. The equation converges to pi squared over 6. But then some people will ask that, what if s equals to -1? Well, what would that be like? Well, I know it kind of violates this limitation right here, but let me just write it out first. So when s equals to -1, this function will basically be like, and if we rewrite this, this is basically 1 plus 2 plus 3 plus 4 plus 5 and so on, so on. So this is actually the sum of all the natural numbers. And what is the result of this then? Many people will thought, well, this is definitely infinity because you're adding a large number every time. But let me tell you what, this is actually equals to negative 1 over 12. So, and this also was proven by Euler. And how did Euler get this number? The ways are not that hard, and let me explain it to you guys. So let's suppose that the sum of all natural numbers equals to a. Let's just suppose that this equation is a. And then let me write another equation, b. What is b? b is 1 minus 2 plus 3 minus 4 plus 5 minus 6 and so on, so on. So this number equals to b. And from the method of using convergence, we can know that b, this equation, this series of mathematical computation equals to 1/4. This is the number that this whole entire series will converge to, 1/4. So now we can apply some of the calculation process. So when a minus b, what would the result be like? Y minus 1, 0. 2 minus negative 2, that's plus 4. 3 minus 3, 0. 4 minus negative 4, that's plus 8, right? And then so on. We can basically know this. And now, this is, if we take a close look, we can realize that 4, this is 4 times 1, right? And 8 is 4 times 2, and this is 4 times 3. So this is basically 4 times the number of 4 times the sum of all the natural numbers added together. So, and also we know that b is 1/4, right? So this basically equals to 4a, right? And this is 1/4. So negative b equals to 3a. And that, which means negative 1/4 equals to 3a. So a equals to negative 1/12. And what is a? A is the sum of all natural numbers. So the sum of all natural numbers equals to 1/12. This is how Euler got that the sum of all natural numbers equals to this specific number. But is this method absolutely accurate? Not necessarily. And now we have to talk about another thing called the Euler's product formula. What this formula tells us is that the zeta function has some connection with the distribution of prime numbers. So Euler basically get this product formula from his zeta function. And how did he get this formula from the zeta function? Let me just briefly explain it here. So first, we have to write out our zeta function. Okay, this is the zeta function. So if we times both sides, okay, we can simply ignore this. So if we time both sides by 1 over 2 to the s power, this side will basically become this, right? And then here it will be this times. Okay, this is the entire thing. And then if we use the original zeta function minus this, if we call the original zeta function a, and this will be b. So what we get is a minus b, okay? And that is the result equals to c. Okay, let's just suppose that the result equals to c. And then if we use c, if we times 1 over 3 to the s power on both sides, okay, so this will be c times this entire thing, right? And then if we use this, the result of a minus b minus 1 over 3 to the s power, the entire thing. So what would that be like? So it basically be this, and this equals to d. And then if we time like this number to d, entire thing. And then we also apply the same method. We use d to minus this entire number. So d minus 1/5 to the s power d, then equals to e. So if we continue to use this process, what can we discover from it? 2, 3, 5, what will be the next one? Definitely 7, right? So this is all the prime numbers. So if we apply infinite amount of prime numbers like this to time the zeta function, this Euler product formula is the result that we're gonna get. So this is basically a capital or uppercase pi, and it basically represents a summation, but instead of adding them all together, this means multiplying them. So it's more like infinite multiplication of this entire thing. And from this Euler's product formula, Euler can see that there is definitely some connection between the zeta function over here, and the distribution of prime numbers. And that introduced to Riemann's zeta function. So let me write out the Riemann zeta function first. Okay, so this is the Riemann zeta function. It might look very complicated. Well, actually it is. And this zeta function is basically a result after Riemann applied a method called analytic continuation to the original zeta function. And what is the analytic continuation? It's basically a method that expands the defined interval of a certain function. So remember that in the original zeta function, s has to be larger than 1. So if we have a coordinates system right here, it has to be all the areas is over here. All the areas that right here cannot be defined, right? And for Riemann's zeta function, Riemann expand the defined interval to all the points except s equals to 1, which means that only at this point, the function is not defined, and all the other points over here and beyond, they are all defined. Well, except for this line, all the other points are defined. So with this, remember that I said the sum of all the natural numbers equals to negative 112 isn't exactly accurate. This is why. Because in the original zeta function, which Euler used, the defined area does not include negative 1. The reason people say that all the natural numbers, the sum of all the natural numbers equal negative 112 is after Riemann has applied his analytic continuation. And using Riemann's zeta function, we can see that, oh, right here when s equals to negative 1, the result will equal to negative 1 over 12. But how exactly does this result equal to negative 1 over 12? This is because that in a complex plane, the result shifts. So when you plug in certain values, like over here, after you do your complicated calculations, the final result might shift over here. So what does that really mean? Let me just plug in certain values, and then you'll see. And right here we have a complex plane. This is the real axis. 1, 2, 3, 4. And this is the imaginary axis, which means I over here. And this is 2i, 3i. Okay? And if we use the original zeta function, if we plug in certain values like 2 plus i, what if s equals 2 plus i? What would that result come? And the entire calculation process is very complicated. And let me just tell you the result. This will be equals to 1.15 minus 0.44 I. That is the result. So what does that really mean? Remember, we plug in this value. Where is this value on the graph? 2, right? That's the real part is 2, and then I. So that's basically the point that we plugged in. But after we calculated our result, this is what we get. And where does that lie? So 1.15, that's basically like over here, right? And it's negative 0.44, so like around here. So that will be our final result. And now it becomes interesting because we plug in a point over here, but then after a calculation, it shifts over here. And also, this is why that when we plug in negative 1 for the after analytic continuation for Riemann zeta function, when we plug in negative 1, the result after the calculation will shift to like negative 112. That's why people say that, oh, the sum of all the natural numbers equals to negative 112, and it isn't exactly accurate. And also, from Riemann's zeta function, after he applied the analytic continuation method, Riemann also got something called a functional equation. And let me write that out too. Okay, so this is Riemann's functional equation. It is even more complicated, yes, I understand. And let me explain certain things in the functional equation. This function, that is called the gamma function. Gamma function is basically applying the factorial to it. So if gamma s basically equals to s minus 1 factorial. So this basically means a factorial. This entire equation is very complicated, but there's only one point that we need to look at. There's only one part. It's this part. Sine. to the pi s over 2. What does this really tell us? So Riemann hypothesis is a hypothesis that Riemann made trying to find the zeros. So when a graph crosses the x-axis, he's trying to find where exactly are those x values when the function equals to 0. So that's what he's trying to find. And now from this part, it's easy for us to see that when s equals to -2, -4, -6, the function would definitely equal to 0. Why? Okay, so if we plug in -2 to it, it will be -2 pi over 2, right? And what is -2 pi over 2? Isn't it sine to the negative pi? And sine negative pi, that's basically 0, right? And if one term equals 0, remember that this is all multiplication. If one term is equal to 0, then all the other terms will definitely equal to 0. So this entire function will equal 0. So when s equals to 2, -2, the function will equal 0. But when s equals to -4, what would that become? That's basically sine -2 pi, right? -2 pi is just turning it one more round, right? Just turning it one more round. So it will still be 0. So basically we can see that all the negative even numbers, -2, -4, -6, those will result in the function equals to 0. How do we call those kind of zeros? These are called the trivial zeros, meaning that they are very, for mathematicians, they are easy to see, they're easy to identify. That's why they call it trivial zeros. And also, Riemann proposed that there is also another kind of zeros called the non-trivial zeros. And what does those mean? It means that those zeros are not as easy to identify as those kind. And Riemann hypothesis basically states that all the non-trivial zeros lies on this line, -2. 1/2. All the non-trivial zero lies over here. That's what he proposed. And you might be wondering that, wait, if all the non-trivial zero lies over here, if I have a point, let's say like over here, how does this like crosses the x-axis? Remember that before we talked about the point shift. What Riemann means is that all the points on this line, on this specific critical line, that's what he called it. On this specific critical line, no matter where it is, no matter where the y value is, after the computation, the entire the entire point would all shift back to 0. They will all shift to 0. And that's his famous Riemann hypothesis. And even up till today, no mathematicians in this world have proven that Riemann hypothesis is true. It's also waiting for more future mathematicians to come and possibly prove that Riemann hypothesis is true. But actually, it doesn't mean that up until this point we have made no improvements. No, we did. So in early the 1900s, I think, mathematicians have proven that all the non-trivial zeros, they lie in this critical strip. So from 0 to 1, all the non-trivial zeros lie over here. But even if they prove that all the non-trivial zero lies over here, they still couldn't prove that all the non-trivial zeros lies exactly upon this line. But now with the help of computers, we can actually prove that, I think, what's that number? 1 trillion non-trivial zeros lie on the the critical line when x equals to 1/2. But even if 1 trillion non-trivial zeros lie on this line, we still cannot say that, oh, all of them lies on this line. We have to prove that it is true. And this is basically what the Riemann hypothesis states. All the non-trivial zeros lies on the line when x equals to 1/2. And up until this point, nobody has proved that Riemann hypothesis is true. If you successfully proven that this Riemann hypothesis is true, you get $1 million US. That's the reward for this. So it's probably one of the hardest way to earn $1 million in this world. But learning what the Riemann hypothesis is actually very interesting, because I'm actually still currently in calculus AB, and when I learned calculus AB, I realized that wow, there's another world that's beyond, the algebra, beyond geometry. But then when I look into what the Riemann hypothesis is, I realize that there is even a wider world that is beyond the realm of calculus. I feel like this is even higher than calculus. This is all the complex plane, imaginary axis. This is all at the level of imagination. This is even more fascinating. This is even more interesting. And I'm happy that you are you have the patience to watch until the end of this video, watching me explaining this Riemann hypothesis. And I just feel like this is a fun concept that I need to share with you guys. So thank you for watching. Be